Hi everyone. In this presentation, I'm going to talk about our final project report on the generation and classification of novel machine learning project ideas. For courses such as machine learning, deep learning, and natural language processing, one of the major challenges is to come up with a problem statement and a project title. In this project, we aim to solve the same problem of generating novel machine learning ideas given a corpus of past project ideas. After this, we also aim to classify a given machine learning idea into different human labeled categories such as NLP, vision, finance, and so on, and categorize it as supervised learning. The dataset that we use in this project consists of all the machine learning project ideas that students at Stanford University submitted over the past 17 years. After extracting these titles, we manually labeled them into 8 different categories, which are NLP, vision, robotics, health, finance, game AI, entertainment, and generic ML. Once the dataset was ready, the next step for us was to pre-process and clean the data. The first step was to remove all the duplicate project titles. Next, we eliminated all the project ideas with less than 3 words. We also tried to remove the stop words such as and, of, the. However, for our use case, this did not make much sense because this resulted in project ideas losing their meanings, which was required for our processing. This slide captures the data representation after we manually tag them into 8 different labels. It can be seen that the data has an uneven spread and generic ML class has the most number of project ideas. Here, we see the top words in each of the different categories according to the TF-IDF. Moving on to the methods and the model architectures that we used. Since we are working with a small data set, we used transfer learning and leveraged existing pre-trained large language models like AWD-LSTM, Transformer, and Transformer XL. The reason behind choosing AWD-LSTM is that it works well with dataset having a sequence of words. And since this is exactly what we needed for our project, we went with this model. Transformer-based large language models have demonstrated impressive capabilities in open text generation, and thus we thought of experimenting with this model as well. The Transformer XL is also based on Transformer, but we have noticed that it is capable of learning longer dependencies and is faster in processing. Traditionally, supervised learning methods have been used for classification problems, and in our project, we use supervised learning to classify a generated or pre-given machine learning project idea. We experimented with random forest classifier, linear SVC, multinomial naive Bayes, and logistic regression, further followed by 2 deep learning models that are based on CNN and transformers. To find the best performing model, we used a cross-validation approach, and we observed that logistic regression has the highest accuracy of 54.71%. To further evaluate the logistic regression model, we calculated other metrics such as balanced accuracy, top one accuracy, etc., which are elaborated on in the results section. Moving on to the deep learning models, we used a CNN-based architecture that has an embedding layer, followed by a convolutional layer, followed by max pooling, and 3 dense layers. The results that we observed included only 4 out of 8 labels and had the top one accuracy of only 34%. This was not expected because in the earlier experiments, we saw that logistic regression had an accuracy of 54, which was more than the deep learning model that we ran experiments for here. The next deep learning model is a transformer-based model where we made use of the BERT model to get the embeddings, and we used the Hugging Face API and 3 dense layers. We observed that this model gave better results with the top one accuracy of 64% and a top 3 accuracy of 89%. Further, we experimented with the same deep learning model and tuned different parameters like the learning rate, decay rate, epochs, and batch size to evaluate results on this. Moving on to the results section. After training the model on the dataset, we generated novel machine learning ideas using the AWT-LSTM, Transformer XL, and Transformer models. After manually verifying the results, we observed that none of them was there in the given sample dataset. The slide here represents the results from the Transformer model. I'm now going to talk about the metrics that we use to evaluate the results obtained using the 3 models. The first one being COLA. COLA is a metric that is used to check the grammatical acceptability of the predicted project idea. It helps to remove those with little semantic meanings. However, there are a few concerns with COLA. The first one being that it gives some false positives. What it means is that an idea could be tagged semantically correct using COLA. However, it might not be treated as an ML project idea. It may also result in some false negative, meaning that an idea gets removed since it has a low semantic score obtained from COLA, but it actually can be treated as an ML project idea. The second metric that we used is the word mover's distance. This metric calculates the distance that a word takes to move itself to another word And thus, the more the distance between the two words, the more dissimilar they are, and thus, the more unique a generated project idea is. The blue score also measures the similarity between a reference and a given candidate sentence. For our use case, we want this score to be as low as possible, and we set a threshold of 0.39 to categorize a sentence as unique or not unique. We use three variants of blue for our projects, which are blue 2, blue 3, and blue 4, where these numbers indicate the number of words that we take to perform the blue score on. Self blue is a metric that is used to quantify the diversity in the generated outputs itself. And for our experiments, we want this score to be as low as possible, which would indicate a higher diversity in the generated text. This table represents a comparative analysis of the different metrics performed on the three different models. COLA represents the number of grammatically correct ideas. WMD represents score of how many of those grammatically correct ideas were unique. The blue score results represent how many of the grammatically correct ideas were unique according to the blue scores, and the self blue scores represent the self blue scores using different variants of blue score. Looking at the table, we can conclude that the results generated by transformer architectures perform poorer as compared to the other two. And we also see that AWD-LSTM took fewer epochs and thus less time to generate good quality results as compared to Transformer XL. Another thing that we analyzed manually was that if we look at the results generated using the AWD-LSTM and Transformer, we see that the sentences generated using the Transformer XL have more meaning and thus are much better as compared to the ones generated by AWD-LSTM. However, the ideas may not be so unique in the Transformer XL as they are in the AWD-LSTM models.
Next, we will look into the results of supervised learning, and first we evaluate the logistic regression model according to different metrics like top one accuracy, balance accuracy, F1 weighted, recall weighted, precision weighted, and Jakarta index weighted. And as we had mentioned, the logistic regression performs better as compared to the other three traditional machine learning approaches, and that's what we have represented over here according to the different metrics. And we also represented classification report, which clearly shows that all the project ideas in the test set have been classified into either one of the 8 categories that we had in the training data set. And the classification report also represents the precision, recall, and F1 score for each of the labels. Next, we also evaluate the CNN-based deep learning model according to the same metrics with an addition of top 3% accuracy, which can be seen in this slide. And after that, we also represent the classification report along with the plots of loss and accuracy over the epochs that we have trained the model for. As you can see clearly from the classification report, only 4 out of 8 labels have the precision, recall, and F1 score, which says that the project ideas in the test data set have not been classified correctly and are classified into either of the 4 labels and not all of the 8 labels, which again says that this model does not perform well as we had expected it to perform. Next, we evaluate the transformer-based deep learning model using the same metrics that we had used for the CNN-based deep learning model. We also do some hyperparameter tuning like changing learning rate, decay rate, epochs, and batch size to get the best model with highest accuracy. And as you can see, the last row represents model with top 1 accuracy of 64% and top 3 accuracy of 89%. The top 1 accuracy of 64% is around 10% boost from the accuracy that we had received in the logistic regression model. If we look at the classification report, we can see that there are values present for precision, recall, and F1 score for all of the 8 labels, which shows that the ideas in the test data set are classified into either one of the 8 labels, which is what we want. And this shows that this particular deep learning model performs better as compared to the CNN-based deep learning model architecture. We also show the plots for model loss and the model top 1 accuracy. To conclude, we would say that after performing different approaches for supervised and unsupervised learning, we have come to the conclusion that the transform-based approaches work better in both the cases. And in the future, we plan to develop an end-to-end pipeline wherein an unsupervised model will generate the machine learning ideas and the supervised model will tag those ideas into different categories.